is very similar, except that this guy is function of x and what? In unsteady. And time. And the right hand side will also be function of x and time. Okay? So we will see that later on. Okay, two typical problems in aerodynamics. Analysis and what? Can you suggest? Not aerodynamics, in engineering. Analysis and what?
Design.
Design, very good. In analysis, you're given what and required what? We're given the problem, we're given the shape, we're given the camber here, right? The camber shape. YC as a function of x, and I'm giving the operating condition. I'm doing an analysis for an existing thing. Operating condition, I mean u infinity and the alpha. So it's as if we're given what here? For this equation, I'm given what? The right hand side, right? Okay? So for the analysis, I'm given the camber shape, I'm given alpha and u infinity, I'm given the entire right hand side, and I want to solve this equation. This is hard, so what's required? The required is the circulation distribution. And actually, consequently, if I have gamma, like I said, I can get the CP and lift, right? So this is an analysis problem, and it's hard. Why it's hard? Because I need to solve what? And what? Integral equation. It's not that straightforward. At least we don't take a course on integral equations in our undergrad. We take a course in differential equation. Every university, engineering university, they teach a course in differential equation, but I'm not aware of one that teaches a course on integral equation in the undergrad era. Okay? So it's not that simple. But anyway, we will do it, of course. We'll do analysis. But what I'm trying to say is that in contrast to our engineering intuition, usually when you have an engineering problem, you can do it either way. You can do it analysis and design, and always the design is the harder problem because you're doing the inverse of something. Okay? Actually, for aerodynamics, typically, 2-dimensional, 3-dimensional, unsteady, it's the other way around. We'll see why. So, given, I mean, you might have seen it now. So here is what is given in the design problem. Can you tell me what's given? Can you guess what's given in the design problem? Very good. No, actually, more than CL. What? The entire pressure distribution. I'm given the desired pressure distribution all over the airfoil. This is very demanding. So the desired, so not only CL, the desired delta CP, which is, I mean, it's very related to gamma. It's as if I have, here is the equation. What is the equation? It's just 2 gamma over u infinity. This is the CP. So if I have my desired pressure distribution or gamma and the desired operating condition, again, u infinity and alpha, what is the required? The required is, what's the camber that will result? What's the camber shape that will result in this pressure distribution? Okay? This is straightforward. Why? If you have gamma as a function of x squared, for example, whatever, you have gamma as a function of x, look at this. So you have the left-hand side. This is the left-hand side. Just put it in the left-hand side, evaluate this integral, so it's x squared over whatever. Get this integral, the result will be a function of x. It immediately gives you the slope of your camber, just integrate it one more time to get y, right? And like I said, if you look at Prandtl's lifting line theory, the integral equation for circulation looks exactly like this one. Very similar, not exactly, very similar to this one. And it's the same structure. If you want to design, this is how we arrive at the elliptic shape of the wing. If we want elliptic distribution, just so you know your gamma, it's an elliptic function. Put it here, get the chord distribution, get the twist distribution, whatever. It's usually like this in aerodynamics, interestingly. So it's the other way around. Design is much easier than analysis. Okay? So here it's easier. Why? Because just evaluate an integral. Any question, please? If you have a question, please stop me. Please, please. Don't let things pass. They already passed. These already passed. You already seen them before. So we're just doing the review. So let us make the review worth it. If you have a question, please stop me. Interestingly, this is the way exactly NASA 6 series camber shape was designed. And this is one of the problems actually in the homework. Now on, maybe most of the homework one was not that educational. Only one problem was educational, the one that you asked about. But all the other homework problems that is now on, they are educational. We're going to learn something from them. So one homework problem that will be assigned in homework 2, which I will release today, we'll talk about it next lecture, is on NASA 6 series. Actually, so like I said, NASA 6 series. The camber shape of NASA 6 series is designed exactly by this equation. To have or to maintain a constant pressure distribution. So maintain a constant gamma distribution. So you have gamma on the left hand side as a constant, get it outside of the integral, do this integral, 1 over x gives you a logarithm, right? So the NASA 6 series actually is a logarithm kind of thing. You integrate it one more to get y. Okay, the camber shape. So this is how NASA 6 series was designed, and this is a problem in homework 2, so I'm not do it in detail here. Any question, please? Any question? So let's do analysis. Because design is easy. You will have a homework problem. Let's do some analysis. Solving an integral equation, which is not an easy thing to do. Any question? Sometimes, actually, we have a very useful formula that is not very well known. It's called Sungin inversion formula. German mathematician. Says that if you have an integral equation in the following form, which turns out to be exactly our form, luckily. So 1 over 2 pi, integral from -1 to 1, so you need to shift your coordinates, of some function f of zeta divided by x minus zeta d zeta equals. So the way an integral equation works, if you have any function named zeta, maybe zeta squared, zeta cubed, 1 over zeta, whatever, and you integrate this guy between limits, so zeta will go away, so the result will be a function of what? Will be a function of what? Come on, guys. The result will be a function of what? If I give you f of zeta function, and you integrate with respect to zeta between limits, the result here will be a function of what? X. Okay. So this is equals some function of x. So for an integral equation like this, I have the right hand side, and I'm looking for the right f that when I do what we said, you get this given g of x. So this is how we interpret the integral equation. Okay? And we're looking for this f. So the guy is giving me the solution. He's saying that f and g must be nice. Okay? In the sense that they have to have finite number of discontinuities. Okay? They cannot be crazy, because mathematicians are very good at devising crazy functions that make your approach fail. Okay? No, we're not. We're excluding those crazy functions. Yes.
Is it an f minus sigma on the top?
F of zeta.
Oh, f of zeta.
Okay. If f of g are nice, but more importantly, f of 1. 1 our problem is the trailing edge, by the way. Okay? And in our problem, what is f? Can you tell me in our problem what's f? Gamma. This is the circulation distribution. Okay? F of F1 must be 0 or finite. Can you tell me what is this in our problem? Gamma of 1. Remember, the pressure distribution is proportional to gamma. So it means that Cp is also 0 or finite. Also, the velocity distribution is proportional to gamma. So the velocity distribution is either 0 or finite at the trailing edge. What does this mean in our... How do you interpret this as an aerodynamicist? This is what? This is the Cotta condition, right? So luckily, if you want to satisfy the Cotta condition and your F and G are nice enough, this guy solved you the problem. Here is it. It's a crazy one. So it's -2/pi, and you will have here the leading edge singularities. It's 1 minus x over 1 plus x times an integral -1 to 1. 1 plus zeta divided 1 minus zeta g of zeta x minus zeta dz. So if g is easy, I can use this formula and solve my problem, right? If g is easy in the sense I can evaluate this integral, I'm done. The guy solved the problem for us. Many thanks, because solving an integral equation is hard. We'll not do it this way. I mean, keep it at your disposal. Sometimes you will encounter a nice g, put it and you're done. We'll do it in a more practical way, okay? Which is the way that you most likely have learned it in your undergraduate course. Any question, please? Any question? The trick is, whenever engineers are stuck in some equation, they do what? You remember? When you're stuck in an equation, PDE, something, integral equation, differential equation, you do what?
Assumption?
Yeah, it's close, but there's a very specific assumption. We do what? Series solution. Whenever we're stuck, we do a series solution. So we will assume a series for gamma as the solution with unknown coefficients, and your problem is to determine the coefficients instead of determining the function. So the series will be in terms of another coordinate. So here is our x, it's from 0 to c. So this is my x. A non-dimensionalized large x will be from 0 to 1, so this is simply x over c. We'll do it in terms of another coordinate. So this is coordinate phi, this angle. So the large x going here from 0 to 1, phi will going from here 0 to pi, okay? And the relation is very easy, is that x over c is large x is 1/2 1 plus cosine phi, okay? So the series will be in terms of this phi, angle phi. That's fine, it's just a coordinate transformation from x. Here is the series solution. We will assume, like Muhammad said, we assume a series solution. That the solution to your problem, you're looking for gamma of x, or alternatively or equivalently gamma of phi. This phi is just equivalent to x. Here it is, it's 2u infinity times, just for non-dimensionalization by u infinity, a naught tan phi over 2, plus this is the heart of the thin airfoil theory, plus summation n equals 1 to infinity, an sine n phi. This is our assumed series solution. So now what is, previously gamma was the unknown function. I assumed it to be of this form. Now what are the unknowns, the new unknowns that I introduced?
A naught, an.
Exactly, the coefficients. So now I'm looking for the coefficients. If you get the coefficients, you're done. Okay? Let's look at this structure. Why these things in particular? What about gamma of 0? So phi equals 0. Phi equals 0 is this what point? Phi equals 0 is what point? Trailing edge, exactly. This substitute phi equals 0 at this expression. Sine 0 is 0, tan 0 is 0. So gamma is 0 at the trailing edge. So this is satisfying what? equator condition. This automatically satisfying the equator condition. Let's get gamma over gamma of pi. Gamma of pi is what? Pi is what? The leading edge. So substitute pi, please. Sign in the pi again is 0. But 10 pi over 2 is what? 10 pi over 2.
Infinity.
10 90 degrees what?
Infinity.
Infinity. So this goes to infinity. This term gives you the leading edge singularity, which we agreed to maintain. It doesn't hurt. Why? Because it's an idealization of a high, very high pressure. That's fine. We can keep it. Actually, we intentionally put this term here to represent the leading edge singularity. Okay? Any question about that? Okay, so let's see how to get the coefficient. So you have your gammas. Where is the equation that I want to satisfy? Here is your integral equation for circulation. So I'm going to substitute here for gammas, and hopefully this will give me infinite number of equations for the coefficients. Okay? So let's do that. So the integral equation for circulation. Please, if you have a question, stop me. Let's do it. So we have 1 over 2 pi integral 0 to c gamma over x minus zeta, right? The gamma here, I will get it from the series solution, 2u infinity a naught tan phi over 2 plus summation an sine n phi. Down there we had x minus x dash. Oh, by the way, this was at dash, at phi, at x dash. This is phi dash, right? Down there we had x minus x dash. So the x is actually half c over 2. So cosine phi minus cosine phi dash. Over there we had dx dash, so this is negative c over 2 sine phi dash d phi dash. Remember, x is 1/2 cosine, so if you differentiate to get dx, so this is actually d little x dash. Okay? We're going to remove some stuff here, c over 2 here from c over 2 there. Okay, now the right hand side. The right hand side was u infinity times alpha minus dy camber by dx as a function. That's all. ui camber by dx.